All right, here we are again with our CPM Integrated 3 Homework Help, Chapter 8, Section 8.3.1. 8.3.1 is a behemoth of a lesson, so this video is going to be a lot longer than the normal video, so buckle up. And as always, I will have corrections in the description of the video. They won't appear there immediately after the video. I usually, after I post, I look through them, I try to find mistakes, and, sometimes I miss stuff while editing, so no corrections doesn't mean there's no mistakes at all. There might be something here and there, but you can be pretty certain that the video is pretty accurate if you don't see any corrections there. If you have any questions or if you see corrections of your own, feel free to leave comments in the comments section and let us begin. Here we have question 8-92. Carlos is always playing games with his graphing calculator, but now his calculator has contracted a virus. The trace, zoom, and window functions on his calculator are not working. He needs to solve x cubed plus 5x squared minus 16x minus 14 equals 0. So he graphs y equals x cubed plus 5x squared minus 16x minus 14 and sees the graph below in standard form in the window below. Here is the window. Part A. From the graph, what number appears to be an integer solution of the equation? An integer is a number that does not have any decimal or fractional components. For example, 3 is an integer, 5 is an integer. 7.2 is not an integer because it has a decimal point. So it's asking what whole number does this have a solution? Here we can see that this tick mark is exactly covered by the line of the graph. So all we need to do is count how many ticks back this goes. I'll zoom this in slightly. So we have 1, 2, 3, 4, 5, 6, 7. This is x equals -7. So our answer should be -7, 0. The second part asks us to verify that our answer to part A is a solution. How do we do this? We need to plug that x value of -7 into this function, and if we do, because it is an intersection on the x-axis, the result should be 0. So, switching over to our canvas window, we have, I didn't actually remember it, x cubed plus x squared minus 16, 14. Okay, x cubed plus 5x squared minus 16x minus 14 equals 0. Is that right? Yes, it is. We have x equals -7. So that'd be -7 cubed plus 5 times -7 squared minus 16 times -7 minus 14, and this should be 0. 7 times 7 is 49. 49 times 7 is 280 plus 49, 229. So this would be -229. And it's negative because -1 times -1 times -1 is -1. Then we have 5 times 49 plus 16 times 7 is 70 plus 42. That's 112 minus 14 equals 0 here. Quickly double check that cube that I've just calculated. Never mind, I wasn't even close. It was 343. Oh well, we live, we learn. So here, 5 times 49 is 200 plus 45 plus 112 minus 14. And then we just have to add all this up. So we have 245 plus 112. I'll do this one first. That gives us 357. Sorry, minus 343 minus 14. This subtraction gives us 14 minus 14 is indeed 0. So we see that plugging 7 into this function gives us 0, which confirms that 7 is a solution to this. Now part C. Since you know a solution to the equation, what is the factor associated with this solution? When it asks for the factor, it basically says if you know that x equals negative 7, what do you need to put into the factored form to get the answer? So that would be x plus 7. So it'd be x plus 7 plus x plus whatever it was, and then it'd be x plus whatever it was, because there's 3 solutions here, but x plus 7 is one of them. So your answer here is x plus 7. Finally, for part D, use polynomial division to determine the other factor. So we write this again. We have x cubed plus 5x squared minus 16x minus 14. And we're dividing this by x plus 7. There is polynomial division. So now we're trying to get this first term to match this first term. And for that, you need to multiply this by x squared. Subtracting. X squared times x is x cubed. X squared plus times positive 7 is 7x squared. Subtracting this gives us 0 minus 2x squared. Now we bring this 16 down, and we do it again. For this x to equal negative 2x squared, we'd need to multiply it by negative 2x. Negative 2x times x is negative 2x squared. And negative 2x times 7 is negative 14x. Then we subtract, this becomes positive, so these two cancel. And now we have 16 plus, because of this negative, which gives us negative 2x. We bring down the minus 14. And finally, for this x to become a negative 2x, we subtract by 2. And that gives us negative 2 times x is 2x. And negative 2 times 7 is negative 14. Doing this, we distribute this negative into here. 2x plus 2x is 0. 14 plus 14 is 0. Apologies, a little under the weather. And that gives us our final answer of x plus 7 times x squared minus 2x minus 2. The final part, determine the other factor. There's a part E. Use your new factor to complete the following equation. You see here that it's giving us the solution for the last one. So here, we need to work with this. For this, we know that you can multiply this out into... is this factorable? No, it's not. This is not factorable, because the only way to get negative 2 is if one of these is negative. So 2 times negative 1 is negative 2, but positive 2 minus 1 does not make sense. And even if we were to flip these, we would see that 1 times negative 2 is negative 2, but negative 2 plus x is negative x. So we cannot factor this using the diamond or regular factoring. We need to use the quadratic formula. So for the quadratic formula, we will use x is equal to Let me first define our a, b, and c. Our a is 1, our b is -2, and our c is also -2. We know that because this is our a, this is our b, and this is our c. So we have x is equal to, let me move this down a little bit, x is equal to -b plus or minus the square root of b squared minus 4ac, and that's all over 2a. Continuing, these two cancel, this becomes a 2, plus or minus, this becomes 4 plus 8 over 2. This becomes 2 plus or minus the square root of 12. The square root of 12 can be rewritten as 4 times 3, which is the same as the square root of 2 squared times 3. And because this is a square, we can pull it out. So we give our final answer here for this particular section of 2 root 3. So I'll rewrite it that way. 2 plus or minus 2 root 3 over 2. And now, because both of these have 2's, we can separate it. And here we see that this becomes a 1, and this becomes a root 3. X equals 1 plus root 3. We can split this now into x equals 1 plus root 3 and x equals 1 minus root 3. Was this what the question was asking us for? I think so. The other part F now, the other factor leads to 2 solutions. What are the 2 solutions? State all 3 solutions to the original equation. Oh, I think I've skipped F here. So our solutions are -7, 1 minus root 3, and 1 plus root 3. This are our solutions. I'm actually curious, what did it say here? Oh, so the step that we did up here, where is it, the long division, this was part E, and all of this work here solving was part F. All right, here we are on question 8-93. Now, Carlos needs to solve 2x cubed plus 3x squared minus 8x plus 3 equals 0. But his calculator will still only create a graph with a standard viewing window. He sees that the graph of y equals 2x cubed plus 3x squared minus 8x plus 3 crosses the x-axis at x equals 1. What are all 3 solutions to 2x cubed plus 3x squared minus 8x plus 3? So like before, we are given the integer, except instead of looking at a graph here, we are given one of them, the integer solution. So I have already written the equation here. All that's left to do is to confirm it by plugging 1 into here. Thankfully, this is really simple, because plugging 1 into any of these x's will cancel it out in a way. In a sense, it doesn't really change anything. So here, 1 cubed is 1, 2 times 1 is 2, x squared is 1, 3 times 1 is 3, x equals 1, so 8 times 1 is 8. It all stays the same. So we have 2 plus 3 minus 8 plus 2. Here we have 2 plus 2 is 4. Oh, not 2, 3. Okay, 2 plus 3 is 5. That plus 3 equals 8. And that minus 8 is 0. So we have confirmed that x equals 1 is a valid solution. Moving on, we can rewrite this in the form of a factor. So if we had y equals x minus 1 would be one of the factors, and here would be the other one. Instead of using polynomial division or polynomial long division, I'm going to be using a method called synthetic division. Synthetic division looks something like this. We're dividing this entire function up here by x minus 1. So you take the opposite of this -1, which is +1, and you place it right up there. Then you write the coefficients of every single one of these x values. So we have 2, we have 3, -8, and +3. And essentially how it goes is you drop the 2, and then you multiply the 2 by the number up here. 2 times 1 is 2, so you put the 2 there. Now you sum this. 3 plus 2 is 5. 5 times 1 is 5, so you put the 5 here. -8 plus 5 is -3. -3 times 1 is -3, so you put the -3 here. And we have here that 3 plus -3 is 0. So our final answer is 2x squared plus 5x minus 3. This bit here is for a remainder. If this number here were to be 1 for some reason, we would have 2x squared plus 5x minus 3 plus 1 over x minus 1. But we have a 0 there, so that term essentially goes away, and we're left with 2x squared plus 5x minus 3. This other term here, y equals x minus 1, 2x squared plus 5x minus 3. Now, let's see, are we able to use factoring to multiply this out? I'm afraid not, because the only two numbers that make this -3 happen are +3 and -1. That's the highest we can get, and that would be 3x minus x, which is positive 2x. That does not equal 5x, and we unfortunately can't go any higher than 2x here with any combinations of these, so we will need to use the quadratic formula. Our a is 2, our b is 5, and our c is -3. X is equal to -5 plus or minus the square root of 5 squared minus 4 times a times c all over 2 times 2. This -5 stays. This becomes plus or minus 25 minus, that's -8 times -3, -24. No, positive 24, right? Because that's 8 times -3. Yeah, positive 24. And that is over 4. We can add those values together to get 49. And lucky us, 49 is a perfect square. So that becomes -5 plus or minus 7 over 4. And then we can split this x into 2, where we have x equals -5 plus 7 over 4, and x equals -5 minus 7 over 4. This one on the left simplifies to 2 over 4, which is x equals 1/2. This one on the right simplifies to, let's see here, -12 over 4, which simplifies to x equals negative, let's see here, 3. That leaves our final solutions as x equals 1, the integer value we were given, 1/2, and -3. All right. Next question, 8-94. Without actually multiplying, decide which of the following polynomials could be the product of x minus 2, x plus 3, x minus 5. Justify your choice. Looking at these, we see that the first term in every single one of these quantities is 1. That's 1x, that's 1x, that's 1x. So the answer could absolutely not be B or D, because for that to be true, one of these would have to have 2x in the front and not just x. Now, looking at the final terms, we see that's -2 times -5 times +3. That is positive 30. The only term here that has positive 30 as the last term here is C. So without multiplying, I can say with a high degree of certainty that C must be the correct answer. And we can prove this by multiplying it out. X minus 2, x plus 5, x minus 5. Minus 2 plus 5 minus 5. So we'd have x minus 2, x plus 5, x minus 3. If I'm not... Oh, it's plus 3 minus 5. Okay. So here we have... I'll do this one first. That leaves us with x squared. That's negative 2 plus 3 plus x minus 6. And this becomes x cubed plus x squared minus 5x squared minus 6x minus 5x plus 30. Adding like terms, that gives us x cubed minus 4x squared minus 11x plus 30. And this matches what we were given here. X cubed minus 4x minus 11 plus 30. 30. All right, now 8-95. We have, consider the equation 5x squared minus 7x minus 6 equals 0. As you complete the parts below, we need to find these. What are the factors of the above? 5x squared minus 7x minus 6. So we have here 5x squared minus 7x plus 6. Let's see, firstly, if there's a way to factor this. Here, let's see, there's a 5x, and there's a regular x. One of them is gotta be, oh shoot, this is minus. What up? Okay, one of these gotta be plus, one of these gotta be minus. Let's try 2 and 3. Does that work? 15, nah, it's too big. Let's try now 3 and 2. That would be negative 10 plus 3. I think that works. Let's test it. 5x squared minus 10x plus 3x minus 6. Okay, so that does work. So basically what I did is I put the 5x and x like this because I know that the only way to make this equal 5 is if the coefficients of these first two quantities multiply to 5. Now, because 5 is a prime, the only way to do that is with 5 and 1. So I put 5x here and x here. Then I know that this last answer is negative 6. The only way to get a negative number is if one of them is positive and if the other one is negative. Then I looked at the number 6. I know that the last two numbers in these quantities have to multiply to 6. So I first tried to do negative 2 and 3, but that failed because, sorry, negative 3 and 2, but that failed because negative 3 times 5 is negative 15x. And then I would add 3x, and that would give me negative 12, which is far too big. But then when I tried negative 2 and positive 3, I got negative 2 times 5, negative 10. 3 times x is x. Negative 10 plus 3 is 7. That's, in a nutshell, how I did it. You could use the diamond problem for this, but alas, we've done it here. So let's set this equal to 0 and start solving for the roots. We have 5x plus 3 equals 0. 5x equals negative 3. X equals negative 3 over 5. And now we have x minus 2 equals 0 and x equals 2. That leaves our final answers of x equals negative 3 over 5, comma 2. That is part A. Moving on to part B, we have what are the solutions to the equation? Oh, look at that. I've done part B. This was A, and this was B. Cool. How are the solutions to the equation related to the leading coefficients and the constant term in the original polynomial? Well, I have already described that. The leading coefficients, which is the 5 here and the 1 here, multiply together to get the leading coefficient of the original polynomial, and the ending terms of each of the factors multiply to the last term of the original polynomial. That is the relationship. All right, now we're on 8-96. First part, what is the inverse of g of x equals quantity x plus 1 squared minus 3? For x is greater than or equal to -1, this part's important, remember that. Sketch graphs of g of x and its inverse on the same set of axes, and then state the domain and range of the inverse function. So let's begin. Here we have g of x equals, what was it again? X plus 1 squared minus 3. Okay, now let's use the CPM method for this one. We have g of x. So first to the x we're adding 1, then we're taking the square of it. This symbol, by the way, is called the carets. You'll see it on your calculator. And then we are subtracting 3. So g prime of x should add 3. Take the second root and then subtract 1. So our g prime of x equals x plus 3 square root minus 1. I'm going to very quickly confirm that this is the correct answer using my own method. Feel free to skip. Or if you want to see how I do this with the method I'm using, feel free to stick along. So what I'm doing first is I'm flipping the x and the y, and I'm basically solving for y. So move the 3 over, and then square root both sides. And now we have y equals the square root of x plus 3 minus 1. The answers match. Okay, we're good. Now, let's graph. Remember that it's asking for the inverse for x is greater than or equal to -1. Here we see greater than or equal to -1. So, when we create our graph and our table, we want to use x values that are greater or equal to than -1. So I'll start with -1, then I'll go to 0, and then I'll do 1, and then I'll do 2, and I think I'll try 3. That might fit. Looking back at the original function, we have -1 plus 1 is 0. That's -3. 1 squared is 1 minus 3, -2. 1 plus 1, 2 squared, 4 minus 3, 1. And that's 2 plus 1, 3 squared is 9. That's 6. 3 plus 1, 4 squared is 16. That gives us 13. So I'm only going to graph the function of g of x. All right. For g of x, we have -1, comma -3. That'd be around about there. I'll do g of x in red, actually. That's -1, comma -3. That'd be about there. 0, comma -2. That's around there. 1, comma 1. About there. And 2, comma 6. And 3, comma 13. Way up there. So graphing this is there. Now I'm going to graph g prime of x using the y values as x and the x values as y. But remember that they're asking for values that are greater than or equal to -1. So this x value doesn't work. This x value doesn't work. Our first value is 1, comma 1, which is there. Then we have 6, comma 2. That's around there. And then we have 13, comma 3. And we can kind of see that as the x value in the function of the inverse approaches -1, we get the square root of 2 minus 1, which is about 1.41 minus 1, which is 0.41. So as this approaches -1, we're going to get something about like there. So we're looking at something like that. Keep in mind that this function here looks a lot longer because of how I've scaled the y. Let me actually get a graphing calculator to better visualize this. Hold up. What was it again? It was x plus 1 squared minus 3. And now we have our g prime, which I'll use f for. It was the square root of x plus 3 minus 1 for x to -1. And see, it's quite similar. See how that works? All right, now that we've done all that graphing, we can solve for the domain of g of x, which we have as x plus 1 squared minus 3. The first thing we see is that we have a technically a domain of all real numbers. All real. But remember, in the question, we have x must be greater than or equal to -1. So coming back here, our domain is not actually all real numbers. Instead, it's x greater than or equal to -1. As for our range, we can try to plot this graph as best we can. And we see that this parabola will never go below -3. So we have our range as y is greater than or equal to -3. If you wanted to write this in interval notation, that would be x in the range -1 to infinity, and the range would be y in -3 to infinity. Sorry, these are supposed to be parentheses. All right, now for g prime of x, we have the square root of x plus 3 minus 1. And one thing to note is that the range of the original becomes the domain of the inverse, and the domain of the original becomes the range of the inverse. I think I repeated myself twice. It's fine, you get the point. So now our domain, as we know it, is the range here. So that would be x greater than or equal to -3. And our range here is the domain of our original, which is y is greater than or equal to -1. If you wanted to write this in interval notation, you would do x in -3 to infinity, and you would do y in -1 to infinity. Just like that. Nice. And we can prove this. The -1, we can plot this as 1, 2, 3. Sorry, we would do 1, 2, 3, comma 1, and this would go here, and you see that it never goes below -1. So we can see that this is correct, and the square root never goes past -3 this way, so we can confirm that this is also correct. Here we are, question 897. Aniki has a sequence of numbers given by the formula t of n equals 4 times 5 to the n. What are the first 3 terms of Aniki's sequence? Let's go over to our canvas and let's begin working on this. So we have t of n equals 4 times 5 to the n. The first 3 terms of this, you'd usually start at n equals 0. So the first term here is t of 0 equals 20, because plugging 0 here, no, not 20. 4. Because 5 to the 0 power is 1, and 4 times 1 equals 4. So the first term is 4. T of 1 equals 20. Now this is 20. And T of 2, which is our third term, is 5 squared. 25 times 4 should be 100. Okay. Toby thinks the number 512,500 is a term in Aniki's sequence. Is he correct? Justify your answer by either giving the term, number, or expressing why it is not in the sequence. So, we can show that this fits by solving this for n. And we can confirm if it works if our final answer n is an integer. So if we end with the whole number, like 5, for example, we know that his answer is correct. So first, let's divide that 4 on both sides of the equation. That gives us, that 4, 78,125 equals 5 to the n. Then let's take the logarithm of both sides. And now we can see that n equals log of 78,125 over log 5. Let's check if this answer is indeed an integer value, because if it is, then we have an answer. Oh, I did ln. Whoopsie. Log 78,125 divided by log of 5. And would you look at that? This equals 7. So he is correct. This 7 is an integer answer. Therefore, 312,500 is in the sequence because we got an integer. The reason we check for integers is because sequences only rely on integers. You cannot plug 0.5 into a sequence. A sequence goes from one number to the next. 1, 2, 3, 4, 5. So if the only way to get 312,500 in this sequence is by plugging a number that is not a whole number, then it can be in the function t of x, where t is continuous, but it cannot be in t of n. But in this case, we see that the n value is an integer whole number. That means it is in the sequence. Finally, we see in part C that Elsia thinks that the number 94,500 is a term in Aniki's sequence. We can use the exact same method to solve for this. It was 94,500 equals 4 times 5 to the n. We have 94,500 divided by 4. That gives us 23,625 equals 5 to the n. And we take the log of both sides. And we get n equals log of 23625 over log 5. Let's see if this is accurate. So we have log of 23625 divided by a log of 5. Just make sure I've typed this all in, and we get an answer of 6.25 approximately. So this is not part of the sequence because this number here is not an integer. Because it's not an integer, it can belong in t of x, and you would get a value of 6.25 if you plugged that number, but it is not in the sequence here. All right, question 8-98. we are asked what is the equation of the line passing through the point -2, 5 that is perpendicular to the line of y equals -5 x plus 2. First, let's remember that to find the slope of a line that is perpendicular to another line, let's say we have y equals -5x, what was it, plus 2. This line has a slope m of -5. To find the slope of the line that is perpendicular to this one, we have to do two things. We have to take the reciprocal of this and then multiply it by -1. So we take the reciprocal and then multiply it by -1. So in this case, our new m is going to equal 1/5. Now we have y equals 1/5 x, and now we need to find a value for b that when plugged into the equation gives us -2, no. We need to find a value for b so that when we plug it in and we plug the values for x and y, we get -2, 5. So what we can do here is plug 5 for y, which is our y value. Remember, our point was -2, 5. So we can put 5 for a y value and set that equal to 1/5 times our x value plus b. So now we solve for b and we write the final equation. Firstly, we have here, we can multiply, not yet. We can subtract this from both sides of the equation. So we have 5 minus 1/5 times -2 equals b. And then we can multiply this together. That gives us 5 plus 2/5 equals b. We can set these denominators equal to each other. That would give us 25/5 plus 2/5, which gives us a final answer of b equals 27/5, or that's 5.4. So b equals 5.4. So now we have our function y equals 1/5 x, not sure I put parentheses there, plus, I'll use 27/5. And just to show that this works, let me use the graphing calculator. So we had y equals -5x plus 2, was it? Yes. And our new function now is y equals 1/5 x plus 27/5. And as you can see, it passes through the point -2, 5 and is perpendicular as it forms a right angle with the original line. The hell? Yeah, there you go. Alrighty, 899. Which of the following binomials could be a factor of x cubed minus 9x plus 19 plus 5? Immediately the one that screams out to me is this one. Why? Because it really looks like this 5 here is a prime. It can only be made up of multiplying 1 and 5. So the fact that this is 5 means that we have an x minus 5 in there somewhere. If that makes sense. Actually, if I'm not mistaken, I actually know all three. It would be x minus 5, and then x minus 1, x plus 1. If I'm not mistaken. Let's check that. I'm really curious to see if I got it. Minus 9x squared plus 19x plus 5. Here we are. Ooh, I was not right. Hey, but look at that. We do have 5 in there. So the answer is this one. Yeah, that one. Moving forward to 8-100, we are asked to now divide x cubed minus 9x squared plus 19x plus 5 by the factor that we chose in the previous problem. If it is a factor, use it and the resulting factor to determine all the roots of the polynomial. If it is not a factor, reconsider your answer to the previous question. Well, we already know that it's x minus 5, so we can immediately begin dividing. So we have x cubed minus 9, 19, minus 9 plus 19x plus 5 equals y. And then now we can use, because it was x minus 5, we can use synthetic division again. It's a lot faster. 1, negative 9, 19, and 5. We put the positive 5 here, and let's begin. We put down the 1, multiply, that gives us positive 5. Add them together, that's negative 4. Multiply by 5, that's negative 20. Sum them, that's negative 1. Multiply, that's negative 5, and that gives us 0. No remainder, and we get x squared minus 4x minus 1. So here we have y equals x minus 5, x squared minus 4x minus 1. Now, let's see. Is it possible at all to factor this? No, because the two values that multiply the negative 1 are positive 1 and negative 1, and you cannot use any combination of numbers to get 4. So we have to use the quadratic formula. X is equal to a equals 1, b equals negative 4, c equals negative 1. X is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. That negative 4 becomes a positive, plus or minus 16 plus 4 over 2. This becomes 4 plus or minus the square root of 20. This square root of 20 can be rewritten as the square root of 4 times 5, which can then be rewritten as 2 squared times 5, which can then be rewritten again to 2 root 5. So now we have 4 plus or minus 2 times the square root of 5 over 2. We can separate these terms for an easier division. And we can see that our x equals 2 plus or minus the square root of 5. So our final x values are x equals the positive 5 that we were already given, the 2 plus root 5, and the 2 minus root 5. Now we can go back to the calculator that we opened up and check if those are the answers. So we have 5 comma 0, that works. 2 plus the square root of 5 comma 0, that works. And then we have 2 minus the square root of 5 comma 0, and that works swimmingly. Now for 8-101, divide each of the polynomials p of x by d of x to find the quotient q of x, and then rewrite the polynomial in the form of p of x equals d of x times q of x plus r. Quickly breaking down what that question means. P of x is our original function. Then we're asked to divide it by d of x, and this r here is our remainder. That tells me that one of these questions is going to have a remainder, and we finally get to see what that looks like. I'm going to do this problem once using synthetic division and once using polynomial long division, just so I can show how that remainder looks using both methods, as I think that will be important to know. Part A, we have p of x equals 2, negative 1, 3, 2x to the 4, negative x cubed, 3x squared, plus 5. Whoa. That goes 4, 2, 1. That goes 4, 2, 1, and then it's plus 5. Our d of x is x minus 1. And we need to find what q of x is. I'm going to use polynomial long division for this one. Let's begin. We have 2x to the 4 minus x squared plus 3x plus 5. And we're dividing by x minus 1. First, we need to get this x to be 2x squared. You do that by multiplying it by 2x cubed. And that subtracted gives us 2x to the 4 minus 2x cubed. This looks a little awkward because we have a cubed here. So what is actually even better is putting a sneaky little plus 0x cubed here. That is going to be extremely helpful. So now it's extremely clear that this becomes 0. This becomes positive because negative, negative, 2x cubed. We bring down this x squared term, and now we need to get this x to be 2x cubed. That would be plus 2x squared. That gives us 2x cubed minus 2x squared. Subtracting this gives us 0 plus x squared. X squared plus 2x squared is 1x squared. We bring down that positive 3x. To get x to equal x squared, we multiply by just x. That gives us x squared minus x. X squared minus x squared is 0. 3x plus, remember minus minus, equals positive 4x. Then we do plus 5. To get this x to equal 5, we multiply by 4, positive 4. So now we're given 4x minus 4. That here will give us 0 plus 9. At this point, this is our remainder, because it's not really a good idea to continue working on this by doing a plus 1 over x 9. This isn't worth it. I don't know why you would do that. So how you would just end this problem is by writing q of x equals 2x cubed plus 2x squared plus x plus 4. And then for p of x, it was asking for the form p of x equals d of x times q of x plus r. So that would look like this. P of x equals our d of x, which we know was x minus 1, our q of x, plus our remainder at the bottom, which we know is 9. And there you go. All right, now for part B, we are given that p of x equals x to the 5th minus 2x cubed plus 1, and d of x equals x minus 3. So I have already written it here. This time I'm going to use synthetic division. I'm going to put a 3 here because this is a negative 3 and we want this to be a positive 3. And it's very tricky, this one, because you have to put a number on top for every single power. You put a 1 for the x to the 5th. There is no x to the 4th term, so you put a 0. Then you put a negative 2 for the x cubed. Then you put a 0 for the x squared and the x, because there's nothing there. And then finally, you put a 1. You drop the 1, multiply by 3, that's 3. Multiply by 3, that's 9. That becomes 7 times 3, 21. 21, because it's 0. This becomes 63. 63. And then this becomes 189, Jesus. And there you go. So now we know that our q of x is equal to x to the 4 plus 3x cubed plus looks terrible, plus 7x squared plus 21x plus 63. Again, they were asking for p of x equals d of x times q of x plus r. In this case, our r is in this little sectioned off area. So we have p of x equals x minus 3 times x to the 4 plus 3x cubed plus 7x squared plus 21 plus 63. And then we add the remainder on the outside, and there you have it.